Welcome. Welcome to Hydro-Dyne's webinar series. We're going to run a live Q&A session after this presentation, before I get started. So the Zoom's Ask a Question feature is enabled. That's a small button in the corner. We'll take the questions and log them, and then answer them at the end. We would also appreciate your feedback by completing a short survey at the end of the webinar. We can use that to improve our presentations moving forward. Thanks again for tuning in. I think 2020 is the year of the webinar. The title of my presentation today is Corrosion Control for Headworks Equipment Design and Fabrication. My name is Tim Mathias. I'm a business developer for Hydro-Dyne Engineering. I've been in the water and wastewater business for 25 years, wastewater for 19. I've been lucky enough to publish a couple papers for the Water Environment Federation, and that's specifically with corrosion. So this topic is something that's near to me. First, who are we? We're Hydro-Dyne Engineering. We're headquartered in Clearwater, Florida. We're a custom engineered manufacturer of screens, screening, handling, and grit removal equipment. We do that for water and wastewater applications, and we've done municipal and industrial applications as well. Our screens are independently certified. We have the highest screening capture ratios in the industry, and that's because we design and fabricate with very tight tolerances. We take a lot of pride in our products. Our products are built and tested under one roof, and we have more than 2,000 installations worldwide. So we have a large installed base. Little summary of our presentation today. I've kind of tuned this to maybe someone newer to the industry, but I wanted to talk about the Headworks first. It's a tough environment, tough neighborhood. Then I wanted to transition to Headworks equipment, talk about best practices. Specifically, we're going to go into pickling and passivation and what that means. When to talk about some material handling, we'll cover some case studies and then have a Q&A session. So let's get started. The Headworks. It's the head. It's the start of the treatment process for wastewater. What does that mean? Typically, it's a concrete structure that's at the highest point of the system. And the Headworks contains the first unit processes. That means screens, screening, handling, or grit removal equipment. And the purpose of the screens is to remove inorganic solids. The type of, or the size of Headworks is variable, and it depends on peak flow, screen types, and water compositions. And I wanted to show a few pictures with this. The top picture shows a Headworks that is not elevated. You can see the screen in the top picture. That's up here with a grit removal and then a pumping section. Many Headworks are elevated. Here's one in the bottom. It's very large, rated to about 20 MGD. And in this case, the pumps then lift water to a higher elevation to flow through the treatment process. Let's show you a couple more. The bottom picture here is a 1 MGD Headworks, so a much smaller system. Same type of design philosophy where we have screens and grit removal equipment, but these are elevated. And the top picture is a larger system still, rated to somewhere around 40 MGD as peak. And again, we have very large equipment, very large pumps, large screens, larger grit removal equipment as needed to process those types of flows. The Headworks is also the end of the collection system. So what is the collection system? That is a network of underground piping moving wastewater for treatment. Typically, a collection system is gravity or pumped wastewater, and that depends on topography of the area. And most collection systems have some portion that is pumped. It's typically not all gravity. So you may ask, well, what does that mean? That means that a system can have many pump stations. Pump station typically has a couple typical features, and that can be an underground tank with a submersible pump, some type of piping, and pump stations can vary depending on size. So it's not uncommon in the flat Gulf Coast to have 3 or 4 pump stations that move water from the user to the treatment plant. The top picture here shows an underground network, and if we remove the soil, it can give you an idea of how large the networks can be. That's a Texas city, by the way. If we think about one of our local cities, say St. Petersburg, Florida, St. Pete has 800 miles of gravity piping, 49 miles of force mains, and I think they run somewhere around 83 pump stations. And that's a medium-sized city. If we go to a larger city, like Houston, Texas, they've listed 6,000 miles of total piping in their sewer collection network. So these systems can be quite large. The bottom picture again shows a typical design. I wanted to show a couple more designs here because they can vary greatly. The bottom picture here shows a dry pump arrangement, small pump station rated to about 50,000 gallons a day max. Bigger still is the top picture, where we have about 2 million gallons a day in that pump station, and you're looking at the top of the concrete tank with a submersible pump and davit crane to move the pumps around. And we can go bigger still. Here's a Texas-sized pump for a Texas treatment plant. And this pump is rated to several million gallons a day. So as you can probably deduce, the screens for the big system then have to be very large. And we vary the screens based on the treatment plant size. Let's talk about the collection system a little bit more. The collection systems is a tough neighborhood. And you'll see the pictures here of corrosion as it shows up in the collection system. And in 1991, US EPA did a report to Congress. 89 cities participated in this survey. $6 billion was spent on sewer rehabilitation. And this is 30 years ago. 32 cities reported sewer collapses. 81% were believed due to hydrogen sulfide corrosion. And 70% of the respondents reported hydrogen sulfide corrosion at the treatment plant. So this is something that's pretty widespread. And you may ask why. There are two sources that I wanted to talk about that directly impact Headworks equipment, and that is biogenic corrosion and corrosion driven by high chloride content. First, biogenic corrosion. We're going to go back to the collection system, and as the Headworks, we are the terminal point of a collection system. And you noticed I talked about pumped wastewater. Pumped wastewater is highly biologically active. It has no contact with air typically. So without oxygen, sulfate-reducing bacteria that reside in the system can take over. And the sulfate reducers can drive bad effects. They take the sulfate, they can then turn it into sulfide, and then turn that into hydrogen sulfide gas. And hydrogen sulfide gas is our problem child. That can cause odors. Exposure by humans can cause blindness and death in great amounts. It causes corrosion in the system and ultimately collapses. We have a small graphic here. Hydrogen sulfide's a gas. It wouldn't be so bad if it stayed in the liquid, but it does not. It comes out of the liquid and manifests itself into the airspace. And we have a graphic on that. So the high corrosion rates show up in concrete structures, concrete pipe, and exposed iron and ductile iron pipe as biogenic corrosion. It goes something like this. Biogenic corrosion is driven by sulfur oxidizing bacteria. So they take the H2S, hydrogen sulfide, as it occurs in the system. They react with air, and they can make sulfuric acid. Now we'll play the graphic. So oxygen is depleted. The sulfate is then converted to sulfide. That then can convert to hydrogen sulfide. And then as a gas, that can then come out of solution in the system with turbulence. And when it does that, the bacteria then can convert that to sulfuric acid. And the sulfuric acid is the real problem. That can then attack iron and concrete piping. And that's how we end up with a pipe that looks like that. And that all ends up at our Headworks. The second type of corrosion that can happen in Headworks equipment are due to high chlorides. Chlorides come in from mainly seawater intrusion. Seawater has a total dissolved solids level of 35,000 parts. Its chloride levels can be greater than 19,000 parts. That can cause problems in the system at certain levels. water softening can also introduce high chlorides. Water softening in some areas with hard water, then the softeners are regenerated with sodium chloride. That can then be introduced to the wastewater system. It can also get in through road salt through the wintertime in northern locations. And it can be entrained in air in coastal facilities. It also can get in, chlorides can also be introduced in the system by industrial blowdown. That means cooling tower or boiler water. Let's go back to the last slide. Here's a good example. It's not our screen, but you can see the pitting caused. This is a coastal screen. And we have pitting caused in the stainless steel by chlorides as they're entrained in air. And we don't want the rust on the screens. Let's talk about requirements. So for screening equipment, we need acid-resistant materials. We need materials that can withstand biogenic corrosion. We have to have chloride-resistant materials potentially. We have to have materials with structural strength. They have to withstand hydraulic loading, potentially be very large sizes. So whatever material we pick has to hold up for a long time. We typically build equipment with a 20-year lifespan. It has to be affordable. So what do? So our materials of construction generally for Headworks equipment is stainless steel. Stainless supports a large size and large flow rates. Stainless can withstand the hydraulic loading that can be put on the equipment. Stainless is acid resistant, and that means it's resistant to biogenic corrosion as that occurs around the headworks. It's resistant to chloride content to a certain extent. Generally has a good price point and a good record over time, but there are a couple caveats. One must pick the right alloy for the right application. Pickling and passivation are needed in the stainless steel fabrication process, and the steel fabrication's got to be managed. We'll talk about that a little bit more. But let's talk about the alloys. There are many alloys for stainless steel. These are different recipes for the steel. The most used is type 304 and 304L. 304L is the same recipe as 304, it's just got low carbon in it. You can look at a recipe list here. 304 has chromium, nickel, manganese. 316 is another higher grade of 300 series stainless steel. It's got more nickel and molybdenum in it. In this case, we look at the chloride levels, and that drives material selection. Stainless steel goes back to the early 20th century. It was discovered in producing gun barrels, and it was determined that steel with a chromium content of greater than 10.5% stood up better over time to corrosion. Let's look at chloride levels. Chloride levels greater than 200 parts per million in the liquid will drive us to fabricate with 316 steel. Higher chlorides may drive other material selection. If we go to seawater, we may do sacrificial zinc anodes and impressed current protection for equipment and kind of treat the equipment like a boat. For higher chlorides with high pressures and temperatures, say that would occur in pulp and paper applications or oil and gas applications, we would then go to duplex stainless alloys. That typically is not a material for a wastewater application. Let's zoom in on the screen a little further here. So stainless steel is used for the structure, covers, motor housing, shafts, sprockets, and control panel. Say we see the structure, sprocket up top, any type of screening structure as it stands. But stainless steel is not the only material that we would use. Some items we don't need the strength, but we need high corrosion resistance, and we can use non-ferrous materials, and that would be ultra-high molecular weight polyethylene and acetyl polymer. These don't corrode, they have high tensile strength, they have low coefficients of friction, meaning they'll move well through the water, and they're used in things like body armor, parachute cord, or biomaterials. So let's look at that a little further. We can use a perforated plate. We have one of those here, and a guide link. Here's a guide link that is machined out of ultra-high molecular weight polyethylene. We have a perforated plate. In this case, this is machined plate with 6mm openings that are used as a screening material. Then we also have spacers in that network that can be machined very precisely and allow the spacing that we design for the skid, for the screen. Let's see how that all works together here. So we have a picture of one of our center flow screens. The flow comes in and goes out the screen. Then what we have is a guide link, the spacers in between lace link supports, and our perforated plate as the screening material to remove inorganic solids. It all works together seamlessly. Let's switch to more of the design. So in this case, we're designing the entire unit for corrosion resistance and reliability. So we have no key parts that are submerged. We want to minimize our wear items in the design process, so we have no metal chain to be adjusted and no neoprene seals to wear out. We generally maintain tight tolerances, so that begins with our design process, and the tight tolerances allow us to have high screen captures. We use solid stainless steel drive sprockets, and we use no process water to unload the screen. We use process water to unload the screen and no brushes that would ultimately wear out over time. The equipment is designed for minimum footprint, and we can add an integral compactor if necessary. And we 3D model the design. That allows us to get a good look at the sub-assemblies needed. All parts need to be pickled and passivated, and it allows us for efficient assembly. And we'll move to assembly here in fabrication next. Just picking the right material is not enough. We have to have controls and processes through our assembly process to make sure we have good corrosion control over time. So the fabrication methods are important. We surface treat the steel. We want to use the correct tools for fabrication and assembly. And our facility is ISO 9000 certified, and I want to talk about that a little bit further on a future slide. But ISO 9000 is a quality program driving formal written procedures for key processes. Let's talk about surface treatment. Pitting is a breakdown of the chromium oxide layer in a steel. This can ultimately lead to failure, material failure in the steel, so it's not a desired property. We can also get crevice corrosion, that's localized attack on a metal surface at a gap. That can also lead to failure in a structure, so we really want to avoid these processes. How do we do that? So for all the stainless steel for the screens produced, we pickle the steel. And pickling is a metal surface treatment used to remove impurities. We remove the iron from the surface of the steel. You may ask, how do we do it? We use strong acid contact. So we use hydrofluoric acid, and that removes the embedded iron in the surface. And here you can see that the dark scale formed during the welding process. That discoloration is a low chromium area, and that's a potential corrosion point over time. After contact with hydrofluoric acid, we get a very clean surface, which then we can use on the next process for surface treatment, which is passivation. So we passivate all the steel. This assists in the formation of a chromium oxide layer that protects the surface. So we use strong acid contact for that as well with nitric acid. So that's used to accelerate the oxidation of the surface layer of the steel. It's not visible on the surface, but we can test to make sure it's there. The oxidation layer is nanometers thick, and it can be damaged. So after we take the time to clean the steel and passivate it, we have to be very careful that we don't damage the surface. Let's talk about the pickling and passivation process a little bit further. There are 3 methods that can be used. We can spray apply the acid to the surface of the steel. We don't really like that. It's not very precise. The operators have to wear PPE. They're exposed to acid. We can apply a pickling paste or gel. Again, this is not very precise. It's not as repeatable. The third method is tank immersion, which is the picture here, which shows assemblies being put into our acid tank. That's the one we use. It's highly effective. All the parts are contacted, so we can make sure we have a good, clean steel with a good oxide layer laying on it. Let's talk about that a little bit further. So the pickling and passivation process used by Hydro-Dyne is a 4-tank process. We pre-clean the steel with a tank 1 immersion. We rinse it with a cleaning residue as tank 2. Then we descale and passivate in a 3rd tank, and that's where we have nitric and hydrofluoric acid contact. We don't use mechanical processes there. We don't believe they're as precise and deliver the results. Tank 4, we remove the residual acid, and then we dry every piece. So every item is pickled and passivated, cover, structure, piping, anything that is attached to the screen. You can see the results here. Before pickling and passivation, we have a dark weld scale. Everything cleans up, and we have a nice, clean, passivated surface after the process is complete. Let's show that a little bit. So in this case, we have our tank 4 rinse. And this is equipment coming out of our rinse tank. It's generally a 25-minute rinse time, and we rinse with DI water. You can see that all the parts would need to be fully drainable, so we can't have liquid hanging up on any part of the screen. And in here, we've got the final product as screen support and covers that are coming out of our rinse tank. So the entire surface area is passivated, is cleaned and passivated, and ultimately corrosion protected. So we've taken all that time to pickle and passivate the steel and dry it. So then when we fabricate further, we want to make sure that we protect that passivation layer. So that means we don't want metal-to-metal contact with dissimilar metals. We really don't want to be scraping or brushing on the steel to interfere with the passivated layer. And we have to use the right tools for assembly. So if we have to hammer on the steel, we would use something like a rubber-coated hammer. And ultimately, we really want to eliminate grinding, welding, cutting after the passivation layer is applied. If the wrong tool is just laying on the surface, that can damage the passivation layer and show up as a rust stain later. So we really have to take the time to fabricate correctly so that that doesn't happen. We have a quality assurance process through our fabrication and passivation process. Our tanks are monitored. We measure the content of the sludge. We make sure we have the adequate content of acid, and we adjust that if necessary. We recycle the water where we can. And ultimately, we didn't come up with this. We're following ASTM guidelines, which are public, which is available to the public. That's standard A380 and standard spec A967. These contain generic instructions for how to correctly pickle and passivate steel. We've taken that and further refined it into our quality operating procedure, and that's part of our ISO 9000, 9001 process. Let's talk about ISO for a second. ISO 9001, we are certified in this area. ISO 9001 is a division of the ISO 9000 umbrella. It's specifically for design and production facilities. So our key processes are formally documented as part of ISO. That means we don't get the 304 and the 316 messed up. We make sure we put the right material in the right places. We have formally documented the pickling and passivation process so that it's controlled and done correctly. We have assembly controls so that our fabricators understand what tools to use in what area. That helps us train people and make sure that the screens are fabricated correctly. And again, in 2015, we were certified against our own procedures. So let's move to a couple highlights here, and then we'll wrap it up. First project highlight is a job we did in Maryland. There were 3 screens, and these were the tallest screens produced. rated to 20 million gallons per day as peak flow. We put these in a 45-foot deep channel. So they're 56-foot tall screens. They're stainless steel link design. In this case, we also included screw conveyors. But as you can see, the screens are tall. They would not fit in the pickling tank. So the screen design has to accommodate that. We have to design in sections, fabricate in sections that can be then pickled and assembled correctly and then tested and shipped as appropriately. The second highlight is a job we did in Australia. In this case, we had several screens. These were seawater intake screens rated to 53 million gallons per day, so they're very large screens. We did a through-flow lace link design and a mesh design for the first set. That's the screen on the right here. The second set, we did a dual flow design, and a dual flow design is where water comes from the outside to the center. These screens were built in 316 stainless with sacrificial anodes and impressed current anodes. So we kind of treated them like the hull of a boat. So let's wrap it up and then we'll take some questions. So in summary, for Headworks equipment corrosion control, the Headworks is a tough neighborhood. We can have very high hydrogen sulfide, high chloride, so we have to use the right materials. We also have to use the best design to make sure those materials fit together and work well together. Then we have to use the right processes so that once we lay down the passivation layer, that is not damaged through the fab, shipping, test processes. So a couple other things that I wanted to add is when choosing a supplier, select a supplier that understands that environment and understands the sensitivity of the corrosion that can happen in the Headworks environment. Ask the supplier for a corrosion control plan. Ask about the processes. We would advocate that you select a supplier with 100% in-house so that there is 100% control of each process, and to make sure that once that passivation layer is laid down, that the steel is then fabricated correctly. ISO certification is also something we would advocate. That's helped to make sure that the processes are formalized and then followed. And please visit the factory. We would always recommend and encourage anyone to do that here. And with that, I thank you for joining us. As a reminder, we would appreciate your feedback in a survey at the end. And if you have any question or anything you'd like to discuss with us, you can reach us at www.hydro-dyne.com. Send us an email at info@hydrodyne.com or give us a call, 813-818-0777. You can reach us on LinkedIn, Facebook, Google us. We're easy to get a hold of. We'll be hosting a few more webinars this week, and please tune in if you would like. And with that, Neil Robinson is our Eastern Region Sales Manager. He's going to serve as my panelist. And if we have any questions, he will be reading those. So yes. Fire away, Neil.
Yes, thank you, Tim. We do have lots of questions here. First one is a really good one, actually. It's actually my question. And I'm just curious, you did a great job, obviously. So I'm curious, when was the last time you actually did a presentation? Because to me, you didn't seem very rusty at all.
Is that a pun?
Oh yeah, maybe that was a pun. Sorry, let's move on. Next question.
Next question.
A real question. I'm just teasing with you to get you loosened up a little bit here, because there are a lot of questions. Can you talk about using the right tools on the job site to prevent further corrosion, or maybe mitigate further corrosion, if you will?
Yeah, the steel shouldn't be contacted with iron, anything iron-based. So we would use a rubber-coated hammer or rubber-coated tool if we would need to move things around. Shouldn't be grinding on any area if necessary. I would say if there maybe is a specific question about a cover or a method that's needed, please consult us and we can maybe guide you through that process. Great question.
Wrenches, he's typing real time as you speak. He's curious specifically about wrenches.
Yeah, in this case, even our nuts and bolts are passivated. So we probably could use that on a nut because we could ultimately cover the nut and turn it as we could probably use a regular wrench if we had to use a field adjustment.
This is an ongoing question, and then we'll move on to the next question. He's referring specifically, he clarified the contractor on site. So that's a good question. You know, we need to think about that. That's real good.
Yeah, it is. We
Think about
typically
that as
would
much
not
as-
use a rubber-coated wrench on site, but in the wrong area, we may advocate for that. We can get back to you with a little bit more guidance there.
Next question. If the plant water has high iron content that will discolor the metal and leave residual iron on the surface, what is the passivation doing for you then? If the plant water has high iron content that will discolor the metal and leave residual iron on the surface, what is the passivation doing for you then?
Typically, once that layer is laid down, we don't see that. We don't see a surface coating. So if the passivation layer is correct, we wouldn't see an iron oxide layer on the surface of the steel over time. You know, even due to iron as it's high in the water content.
Gotcha.
Hopefully that answered the question.
Yes. Next question. Let's keep rolling here. Thank you. What is simply the difference between pickling and passivating? Because it kind of sounds like it's used synonymously.
They are used interchangeably at times. If you consult the ASTM spec, they actually call the pickling process a cleaning process. It's not really referred to as pickling. So pickling is more of a cleaning process. We're lifting the iron off the surface. That's again contact with hydrofluoric acid. The passivation process is contact with nitric acid to lay down an oxidation layer. So they are separate. We do them, and the ASTM spec allows that to be done in one tank. But that's a great question. They're separate processes that have separate materials required.
Cool. Here, let's keep going. This is rapid fire. The questions are coming in. What about removal of gearboxes to replace a broken unit? The gearbox is not being passivated per se.
Yeah, in case with the gearbox, typically those are cast, if I remember right. So we would replace with a new cast unit. Those typically are very thick steel, last very long time. That is one item that I don't believe that item is pickled or passivated.
Right.
We buy
It's
that steel
correct.
and then hang it on the screen.
Yep.
They're very well-built units that have proven well over time.
Okay, next question. What is the correct metal to use for high H2S or H2S concentrations?
Typically that's a great question. Typically 304 will hold up at high H2S concentrations. Many of our screens are built as 304. We would go to 316 for high chlorides. So all of our coastal screens in the area where we're, say, near the bay or near a brackish water source, we would upgrade to 316 as we would have potential for seawater intrusion or even seawater as it's entrained in the air. We typically don't want rust to show up on the screen at any time. I was looking or surveying the screen in the town where I live. We had put one in there in 2017. That screen was built as 316, and the screen steel had no rust formation on it. The steel looked very clean, very nice over time. That's the kind of wear we like to see. No pitting, no iron formation, clean stainless steel, 5, 10, 20 years down the line.
Okay, thank you. Let's keep rolling here. A couple more. I'm not making these up, Tim. These are some good questions. Is there, if there are low oxygen levels in the water, can this lead to degradation of the oxide layer? Can low oxygen levels in the water lead to degradation of the oxide layer?
That's a great question. Many collection systems deal with a lot of pumped wastewater. Pumped wastewater is classically low in oxygen as it moves through a full pipe. And we haven't seen that. We haven't seen low oxygen levels destroy the stainless steel on the screen. So the screens S304 and 316 have held up well over time in that environment.
Does Hydro-Dyne do grit removal systems? This person has noted that they've seen classifiers that are completely corroded.
Yes, we do, and those are also built out of stainless steel as well.
Okay, maybe there's a lot of questions here, Tim. This is great. This is really your good answer of these questions. Can you not passivate or pickle in the field if you had to get wrenches or impact sockets used for repair in the field?
Yes, this can be done. The two methods that we covered were more field related. That is using a pickling or passivation spray or a paste. There's also another method called wanding, which can be done. So yes, there are localized localized methods for that if a certain area of the steel had to be cleaned up for whatever reason. It's not something that we would typically do.
Correct. Next question. Does Hydro-Dyne use carbon steel?
We do not use carbon steel. Carbon steel can have pitting corrosion, and that can happen very quickly in the sulfide under acid attack environment. So that's not a material that's really appropriate for screens for us and screenings handling equipment.
We've got a lot. What am I going to ask you next here?
Keep them coming.
Can citric acid be used to clean or passivate the screen? And I guess the follow-up question, does Hydro-Dyne use citric acid to passivate screens?
Another good question. So the ASTM spec mentions citric acid as a cleaner. We typically do not use that. We use an industrial surfactant to clean the steel. That's worked well for us and done a better job over time than citric acid. So I would say we don't use it. It can be used by the spec. There are several other methods, say for mechanically cleaning, blah, blah. So we have chosen our process for the best results, and generally that's the tank immersion process.
Okay, very good. Let's keep rolling, maybe one or two more here. Pretty straightforward. Do you have any suggestions for getting rid of H2S common in the Headworks?
That's a whole subject unto itself. Yes, vapor phase removal can be used. You can treat the vapors as they come off the Headworks. There are certain chemical techniques to take out H2S as it occurs at pump stations throughout the collection system. Yes, so oxidizers and different materials are typically used for that and have a long history in the wastewater collection system. So feel free to maybe send me a side email if you have a question on that, and I can refer you to the right person or persons that would help you with that.
Yeah, I think we ran you pretty good through the ringer there. So we'll answer any more questions online as they come in. If you have more questions, you can just simply email us at info@hydrodyne.com, where there's a dash between the hydro and the dyne. So info@hydrodyne.com for emails. Of course, you can go to our website where we have our phone number and lots of information there. You can go to live.hydrodyne.com to see the schedule for the rest of the week on our webinars. And from there, I'll sign off and let you.
Thank you, Neil.
Yeah.
Thanks, everyone, for attending. We really appreciate it. And hopefully this week is a good week for you. Please email us or call us any way, shape, or form. If you have a further question, we'd be happy to answer it. Thanks.